My name is Akshit. I'm going to tell you today about some work that we did with in collaboration with Pankaj Mehta, which concerns this linear response theory of ecosystems. So one of the central questions in ecology is how ecosystems respond to environmental perturbations, to perturbations in the environment around them. And this is, of course, important both for practical reasons as well as theoretical reasons. For sort of practical reasons, one of the most central questions in ecology is, what happens if the temperature or, some other variable in the environment, for instance, the supply of some resources changes? What happens to the state of the system? For instance, the sort of abundances of various species. And of course, theoretically, we know that linear response is a key way that we have in physics to understand systems of any and all kinds. And I would say in ecology, we do have a tradition of doing linear response theory, but typically it's studied by perturbing the sort of various species in the system and then asking if the system is stable or not. But what we're still lacking is a framework for sort of assessing the response of these systems to perturbations in the environment and not species. And that's what I'm going to try and do in the next few minutes, just to give you a taste. And we're going to do it in the context of these consumer resource models, the simplest of which is these set of models due to MacArthur. And the idea of these models is basically that there is a large number of species, all with abundances n, and there's a large number of resources that these species are consuming. These resources are provided from the environment at some different supply rates. These species all consume these resources at some rate that's given by this consumption matrix C, and then they die at some other set of mortality rates. And so to describe the system mathematically, you essentially write down two sets of coupled differential equations. One set is you write an equation for every species I, and what this equation is essentially saying is that these species grow exponentially by consuming resources. And the C matrix sort of encodes which species eats which resource. And by eating these resources, they're able to beat some mortality rate. So you have one equation for each species. So if you have S species, S equations. And similarly, you write down a set of equations for all of these different resources in the problem. And what these equations are essentially saying is that these resources are supplied at some rates. In the absence of any species, these resources go to that supply rate concentration at steady state. And in the presence of these various species, they're all depleted by species, and the depletion or impact of resources by species is given by some other matrix, which we call E. And so just to sort of bring to your attention, one way to talk about environmental perturbations in this model is to perturb these two things, K alpha, which is the supply of resources, and Mi, which is the mortality rate, or sort of how harsh the environment is for species. And the sort of abundances of species and resources are the response variables that we're interested in. So what we're going to be interested in is to change these mortality rates and supply and sort of supply rates of different species, and look at the responses in terms of how the steady state abundances of different resources and the steady state abundances of different species change. And we know that for any linear response theory, the key objects that we need to compute are these things that we call the susceptibilities or the responses. And in principle, this is going to be a 2x2 block matrix, right? And so, for this model, it turns out that the steady states are linear. And so you can do straightforward linear algebra by sort of inverting this 2x2 block matrix to end up with what these responses are in terms of these environmental perturbations. And so what I mean to say is that you can calculate these susceptibilities exactly. These formulas and what they are not so important. The only thing I'll bring to your attention is that there are various matrices or compositions of matrices that emerge by doing this linear response theory, and one of these matrices are what we sort of famously can think of as the effective species interaction matrix. That's composed in terms of the consumption and the impact. Okay, so that's a linear response theory, but what does it tell us? Well, one thing that it tells us is that there's a rather nice way of interpreting these responses or the solutions to these equations in terms of some sort of geometry. And what the sort of geometry is saying is that there essentially are response variables and our perturbations represent 4 different kinds of vectors which live in 4 distinct vector spaces. And if you want to talk about what the response of, for instance, the changes in the species abundances are to the various environmental perturbations you make, well then these sort of composite matrices represent transformations which take some of these vectors to the response space. Just to sort of give you a sense, these are my 4 vector spaces that I'm sort of talking about. There's a space for the species abundances, for the resource abundances, for the species fluxes, and for the resource fluxes. And so all 4 of our things, the steady state species abundances and resource abundances, live in the spaces on top, and the fluxes or the rates live in the bottom. And what our solutions are essentially telling us is that you can look at the responses in species abundance space by taking your perturbations in mortality and supply space through these effective transformations. And so in fact you can write down very much like GR these as upper and lower spaces and convert all of this to Einstein notation. Just in the last minute that I have left, I'll just tell you what the geometry of these solutions kind of looks like. So there's one way to understand the geometry of species space is that in this sort of species abundance space where each axis represents how much species 1, 2, and 3 respond by in their abundance, that's really composed as a vector sum of 2 things. One is a vector which is a composite vector, which tells you how much the effect comes from supply. The other one tells you how much you would die by because of changes in the effective mortality rate. Similarly, you can look at the geometry of resource space. This one is slightly more interesting. So here again, we have the axes which represent the changes in the abundance of resource 1, 2, and 3, and so on and so forth. And what this solution means is that there are again 2 vectors that you sum up. The first one is saying take whatever perturbation to your resource supply was. This P turns out to actually be a projector. And so really what you're doing is that you're projecting the resource supply onto the image of all the consumable resources. That's one of those vectors. And the other vector, which is this one, just tells you basically how much the species, how many resources species leave behind because they're being killed, because there's more mortality. And really all of the resources that are left behind are either because species can't eat them because they die, or because species can't eat them at all. They're unutilizable. And so the steady state resource concentration is just a vector sum of these 2 things. The Siri makes accurate predictions. I won't get into it. If it didn't, then I wouldn't be telling you this talk. And just I'll summarize very quickly. So in this talk, we developed a linear response theory of ecosystems to perturbations. We learned that susceptibilities are the key quantities that connect these perturbations to the response of the system. Geometrically, you can understand the susceptibilities as these composite transformations that take you across these 4 vector spaces. And actually, it turns out that there's a very nice ecological variables that you can interpret through this geometry. For instance, there's a nicer interpretations of niches, there's nice interpretations of various kinds of things that people care about. And then what I didn't tell you, but what is also true, is that you can go away from these linear models that I was talking about in this talk and show that this geometry is actually potentially universal, and it generalizes to arbitrary models of this kind. With that, I thank you for your attention. I'm happy to take any questions.
Questions?
So in this model, your species, different species are just competing for the resources. There is no prey-predator kind of interaction between the species.
No, that's not the case. And typically, as we see in the world, those prey-to-prey interactions among all of the other interactions are actually very small in terms of their frequency.
Any other questions?
So I guess you're in some sense looking at the fixed point and looking at small perturbations around the fixed
That's right.
point. But I guess this is not capturing like dynamical responses, right? Like you could also
yeah, you're mapping steady states to steady states. So you have your system in one steady state, which corresponds to some environmental vector. you change the environmental vector, you go to a new steady state, and then that will happen asymptotically in principle. So you're just asking how the steady states are related to each other. Yeah.
So what's the difference between environmental perturbation and the species perturbation?
You mean mathematically?
Yeah, so what would you do? Like the similar
Yeah, so
equations and
yeah, correct. So here we were varying the supply rates and the mortality rates to look at environmental perturbations. If we were looking at just species or resource perturbations, you would just straight up change the N and R, right? So you're at some fixed point where you have the species abundances at some state. You'll just perturb them all by a small amount, and then you can just ask a dynamical question of whether you come back or you don't come back, right? Which is to say whether the state is stable or not. So in species perturbations, you're not changing the environmental parameters, you're only looking at what's happening to the response variables.
Any other questions?
Yeah.
Are there any restrictions on this coefficient Ci alpha, like you've assumed that A is invertible and all that?
Yes, that's an important question. Yes, so here we assume that actually, so A is invertible. And in principle, it might not be invertible. For instance, it might be the case that you have steady states where species go extinct. And in that case, you have to do some complicated perturbation theory, and you can still deal with that system. So in principle, all of these equations will still apply. You'll just change your A from the original A, which is composed of all species, to just the subset of species that survive. Yes, but that's an important point. Thank you for bringing it up.
Okay, let us thank the speaker once again.